more paper here, so I'm going to just go here. Say side. Anybody do experiments here? Nobody. This is my company. No. I used to do experiments. I just don't have the, it's weird, I don't have the aptitude for it. Like, I go in a lab and spend hours like getting this experiment ready, and then it goes wrong, and it just frustrates me so much that I'm like, I'm not doing this anymore. But I can debug code for 3 days, like, and just focus on it, and then I finally get it. Yes, and it's so rewarding. But I just don't get that same feeling when I do experiments. So, yeah, kind of moved away from it. Okay, well, even if you're not an experimentalist, but this is particularly true if you're an experimentalist, and that is, please label your strain. I'm probably going to be on some of your PhD committees. If you show a stress strain plot and you don't label your strain, I'm going to call you out for it. Because I told you right now, label your strain, and I'm going to show you why. Right? How often do you see people produce stress strain plots, and at the bottom they say engineering strain or logarithmic strain? Rarely. Don't do that. Because let's consider a lambda of 1.01000. And I wrote those 3 zeros behind the 1 on purpose. I'm implying, when I write those 3 zeros, I'm implying that when I went to the lab, I measured it to that level of accuracy. So I measured it to 6 significant digits. All right? Let's just take a look with that lambda of what, if I compute the engineering strain with that lambda, remember that's lambda minus 1, then I get 0.01000. Right? If I compute the log strain, the natural log of lambda, then I get 0.00990. Okay. If you don't label your strain, if you just say strain, and I see that number, then I got to round off to that. I could round off to there because you're throwing away significant digits. Because you don't tell me what strain it is, I don't know, and I'm going to round off. And it's just, basically the two numbers are the same if I round off, right? So there's only like 1.5% difference between the two numbers. But I'm throwing away significant digits by not telling you what strain it is, because I don't know. If you don't label your strain, and then I don't know if it's the engineering strain or log strain. I can't, all that work you did to measure it to 5 significant digits, 6 significant digits doesn't mean anything to me. So label your strain, and I've got an example, and I'm sorry about the quality of this plot. I had to take a screen capture of it, but let me just show you. This wasn't. I was involved in this experiment. It was back when I was at Sandia. So this is an actual stress strain test done on a piece of 304L stainless steel. So stainless steel is very ductile, right? So, in undergraduate you learn that all materials are just linear elastic, right? That's the linear elastic portion of that material. The first 1% of deformation. Who thinks rocks are linear elastic? I know you've all been taught that in undergraduate. Geomechanics, all the problems you solve with linear elastic rocks. When you confine a rock, you put earth around it, bury it in the ground, it can flow like that. I promise you. Rocks are not linear elastic. So anyway, this is steel, right? But in these two plots, this is the engineering strain, that's the true strain. And of course, only the engineering strain was measured, and then the conversion was done to that. So if you don't label your strain, I mean, look at right here. If you just tell me, if you just write strain, and I think it's the engineering strain, but it's actually the true strain, or vice, if I think it's the true strain, and it's actually the engineering strain, then I could be off by like 50%. Label your strain.
And we have two kind of strain. How we select which strain we gonna use or present?
Doesn't matter. I told you that earlier. It's arbitrary as long as you're consistent, right? So that for every strain measure, there's a corresponding energy conjugate stress measure, and as long as you use them consistently, it's okay. Yeah. But you also need. I mean, you're going to get your data from somewhere, right? And so you need to understand where the data comes from and what actually what is presented in the data. That matters much more, like, because you're going to need to get data, stress strain data, to get material properties like Young's modulus and other things like that. And you need to understand what in the experiment what they're actually presenting to you. So it's much more important in the computation. Things will just work out because we're going to make formulations that are energy conjugate and consistent, right? It's really okay when you're taking experimental data to use as inputs for your computation. That's when you kind of need to understand what exactly you're doing, right? And by the way, I heard you say there's 3 measurements of strain. Now, I presented 3 measurements of strain. There's infinite numbers of strain measurements, right? Because it just depends on what you normalize with, right? You can normalize with the initial length. You can normalize with the final length. You can normalize with the instantaneous length. You can normalize with the length of that wall over there. It doesn't really matter. I mean, no one does that, but.